go through some of them, and some I'll just comment so that you can continue with it. And these are not really our focus, but it's also important that you know this. Other than that, as I said, when you go out and you are providing consultancy and so forth, you won't really be doing those simulation studies that much. It's usually the basic statistics and so forth. So it is important that once you hold a master's degree, you should be in a position to do some of this. That's why we are finding we are using so much of our time on that. So that should be it. So we'll do this tutorial, but I hope that from next week I should be in a position to now get to those estimation issues and so forth, so which will be good for your thesis and your PhD studies later on. Okay, so so this is just basically an undergraduate stuff, but I want us to be able to go through and see the programming aspect and also refresh ourselves with some of the statistical issues in there. Okay, so let me share my screen. Okay, so I'm going to read the work. How did I save it? Okay. Save. Just a moment. STAT621 2024. Okay, so the first question is that we want to consider the delta ont data in the R package FSA. So once we say that, then the first thing you need to do is to look for, if you have, in this case I say install, so you need to install the package FS data. So how do you do that? Well, you go here to the CRAN. If you are connected to the internet, you start typing FSA, and this is the data. So you collect, you select this, then you click on install. I already have FSA data installed, so I'm not going to go through it again. But once you click install and you are connected to the internet, this will appear. Okay, now, so once that is done, then you need to now come to here. You need to load it. So it means you need to take it like I have done over there. Now, once you do that, then you will be in a position to do what? To have access to that data. All right. So how do I now? I'll start typing. Is that? So there it is. Okay. Now I can use the help files to check what it is. So it says ages and length of channel data from 2 locations. These are fisheries. Okay, it's fishery science. The package is about fisheries. Yes. You cannot see the screen. Hello?
Yes, sir.
I think I can. Probably it's an issue with the internet.
Yeah, so it's sometimes you need to log out and log in again. I think especially when you are using mobile phone sometimes. But the others you can see, right?
Yes, sir.
Okay. But we have only 5 people. Where are the rest? Okay. Let's hope that they join. Okay, so let's move on. Okay, so that's a help file. So this will give you some idea about what the data is about. Okay, to length and so forth. Okay, so then we go to the question. It says that describe the data. So the description, you can get it from here, right? So if you were to in an exam, you can copy this, right, up to here and modify it to suit what you are going to do. Okay, so just it's what the description is on. They are this is a data set in the FSA. It consists of ages and length of channel data from 2 locations, right? When you come here, to give you the locations itself. Okay, and then the data is stored as what? A data frame in now, which means it's rectangular, and it has 3 variables. The variables are what? Age, which is otolith's age at capture, at the time they captured the fish, and then TL is the total length, and the river is the location of the capture, and that's either salmon or what? Trent rivers. So 2 of them. Okay, and they are this. Okay, all right. So when you want to use it, you can also use this data, right? When we use that, what do we do? When you run this, it makes it available to you. So in this case, you can even get the variable straight away from it. Okay, so that will be the first part. Is everybody okay with this? A, describe the data. So we've described the data. B is what is the size of the data. So the size of the data, you can even get it from here. It tells you that it's a data frame with what? So A description, right? Which we can get from whatever. Then the B is what is the size. So the size, it says is what? It will be a 54 by 3. A data frame made up of a 2-dimensional array, which is a data frame, and it's made up of 54 observations and what? 3 variables. Now, another way to look at this is that you can also use the dim, which is the dimension. So dim is the dimension. If we do that, it will give us 54 by 3 as well, like that. Okay, so that's it. That's how you can show what the size is. Okay, please, you stop me at any point in time if you need to ask a question. Okay, so let's move on to the C, right? The C is what? Construct a scatter plot of the total length at capture as the dependent variable, and then the age as the predictor variable. So here we are testing whether you can plot a scatter plot, and we've done some of this. So plot, scatter plot. C is scatter plot. So what do we do? Well, we know y and x, so you can just do plot, right? And then maybe you choose this one. So you can come here and pick up this. Maybe the first 3 is fine. You put it over here. So what is x? X, we said, is what? The age, right? The description has been given. So x is the age. Okay, so I'll call the data, no, that. Then age, right? Okay. And then what will be y? What is y? So age is a predictor and y is what? The dependent variable is y. What is what? The length, right? Yeah, so TL. And points is P. So this, we can run it like this. It doesn't, we need to then do some more stuff. For example, the math to get it done in this way. And then label the axis as well. So S lab will be what? Age. And the age, we can go back to the help files and see what the age is. So all these are needed. If I'm marking, I'm looking at all. It's age in what? In years. So you can put it there. Age in years. And then what is Y? The Y label. Y lab. Right. So we want a total length. And length is in what? It's in millimeter. In millimeter. Like that. Okay. So I think this is okay for us to. And it looks like that. Oh, total. The total did not come. The T, I should say. Like that. Okay. So this basically will look. And what can you say about the relationship between the age and the length?
There's a positive relationship between the age and the length.
Yeah. As the age increases, it's like the length also increases. But what can you say about these ones? The way this is done. So it's like the ages, the age in years. They did not look at months. It's just 1 year, 2 years. So they are whole numbers. So you see that they are clustered. So we can even be analyzing the variation between the ages of the length for ages. For, let's say, A2. When you go to A3, you have a set of variation within it. But only 5. One was 5 years old. So basically, that's what. So this part, I'm just checking whether you can plot and be able to comment on it. Please, any question? Okay. D is just about I said selecting color for each location. They were called. Also provide legend. So, well, okay. So what if you go back to the location? There are 2, right? Okay. So there are several ways you can do this. Okay. Let's see. One way to do this is that you can plot the first one, which is okay. Let me do one. There are several ways you can do this, as I said. One way, so D. Do you know what I want you to do? So remember that here we've done it, but we don't know which one. Let's look at the data first. If I display this data, you see there are the where they were caught. River, there are 2 rivers. So we want to be able to plot such that all salmon, those that were caught in salmon, are given what? A particular color. And those that were caught in Trent are also given another color. Okay, so that's it. That basically that's what we want to do. Okay. Now, so how do you go about this? Well, I can let's say select. Okay, so let me do that. What that's also will do our selection. So I can say salmon will be so I'll call this data. So if you remember what you did on this, then I'm going to river equal to salmon. So I'm selecting all rows with this as salmon. Now look at this. So you see only salmon is shown, right? Okay. So it means that the other one will be what is it? Trent rivers. So that I can also, so I can just copy this and negate the, because they are 2, I can just put this one here. Or alternatively, we will say that it's equal to Trent, whatever. So it's up to you to decide. So if I do this, you see they are all Trent. The river is only Trent. Okay. So if I have these ones, then I can plot the first one. But what I'm going to do is that the length, remember age is 1, 2, 3 up to what? It was up to 5, if you remember. So let's go to the plot. It's up to 5. Okay, so if I do it, I will limit it to 1 and 5. Okay, so that I have, and then I'll superimpose another one on it. So the first one, maybe I want to plot salmon. So the same way we did this one, I'll call this this. So instead of that one date, I'm going to put salmon. Okay. But I'm adding S lim because I don't know whether, because I will superimpose the other. So supposing, let's say I put, okay, let me just plot that one first before I do that comment. So let me plot this and let's see. Okay, so you see now we have 1.5, 2 point, and so forth. But previously it wasn't like that. And remember that there was 5, but there's no 5 in that one. Yeah, so once I have this limit, I need to do it in such a way that I have 1 up to 5 so that it will accommodate the Trent River, the Trent River data. So when I do this, if you go to, we have Y lim and S lim. So in this case, I need limit for the X, right? I have to even check the Y. The Y is basically the same, so nothing really changes. So I can leave it like that. Wait, let's see. Okay, age in years. Yeah, 40 to 60 is the same thing. Okay. So, but this one I can do 1 to, or even 0 to 5. It doesn't matter, 0 to 5. Okay, so in that case, I'll have something like that. If I want it from 1 to 5, I can also do it like that. Okay. But the next one, I want to now, I needed to color it, right? So maybe this one we color it is black, okay? So do we want to maybe red? Okay, then the next one will make it blue. Okay, so but the next one, because I want to superimpose it, I'm going to use points and not plot. If I use plot, it will do another plot. So I can copy the same thing and use a trend, but I'm going to change this to points. So points, it means I just want, because it's scalar, then this will also be trend, right? Okay, and then I have it. Then maybe their color, I change it to maybe blue. Okay, so I don't need S lab, Y lab, or the stuff. I don't need it, so I can delete all of them. Okay. So that's it. You see, it has superimposed it on it. And I can put a legend if I want. Okay, so legend. Okay, so if you want to put a legend, you can. Is the legend, so you can do this and study how legend. So we can specify what X and Y to use, legend, and then fill and what have you. Okay, so I can copy just a few observations, and then I try and put it back in. Okay. We did not use lines. This, so I can take all of them off. A color. Yeah, we use color. So the color, I need to state the color. So see, it was what? Red. The first one was red, and then we have what? Blue. Blue should be small letter blue. Border black. Okay, that one is we can. It's even default, so we can take it off. Okay, then where do I want to put it? I come to the plot. You see, it will be better at the top, either bottom right or top left. So maybe we put it at the top left. So in that case, I'll delete this. But you can also specify, maybe I want to put it at position 1 and 55. You can do it. That will be at that section. But it also understands, I understand top left, top right, and so forth. So I can delete X and Y and put, I can delete it and put top left. Okay, good. Then what legend? What is the legend we want to put there? The legends will be about what? The river type, right? Where they were caught. So we had salmon. Which red is the salmon, right? And then blue is what? If you don't let it match, you are not going to get it. It will be the other one is trend. It's just trend. So let's take the river of trend. Okay, so let's see. You can, all these you can go and check. Yeah, if specified this, so recommend the core boxes to be filled with a specified color. So should it? What? Yeah, sometimes fill, not no. Okay, let me see. I want to check the value. Okay. So, yeah, okay. I can also fill and gray colors. Okay, let me leave it now and let's see what happens. But it won't fill it with colors. Yeah. Okay. So we need to specify the fill, right? And I can just give it let me see. It won't work. No. It should be okay, 1 and 2. Will they work? Yeah. Oh, no. It has to be the colors. So, yeah, this will be red is 2, blue is 3, I think. No. Okay. Points. 1 to 10. Color 1 to 10. Or let me just 1 to 10, yeah. So let me see. Oh, not points. Oh, I want to do plot and see the colors. 1 is black, 2 is red, but let's see. Blue is 4. Okay, sorry. 2 and 4. Okay, so I can go back and get this done again, and then I can do my legends. Yeah, that's it. Okay, so that's a legend, and then we have it like this. So that's one method. We can find other methods, but we will just be wasting our time on the same question. Okay, but I went through this because one, it will go through selection methods, which is also good for you to know. So this is how you select observations predefined by some characteristics, right? And then I do a plot. I can now superimpose another plot on it. We can now do legends as well, and so forth. Any question on this? Any question? Yes.
Please, I think I have a question.
Yes, if you please.
Say you are in an exam setting. You see, you can also use GG plus for this one.
That's it.
Yeah. And then pass the river type as a mapping.
As a mapping, yeah. Yeah. That's easy. But I usually will not teach GG plot because I want you to get the basis and then you build upon it. But that's the easiest way to do it. Yeah.
All right. All right. Thank
you. In exams, you are free to use it.
Okay.
Thank you. If you know how to use it. That's why I said for plots, you need to do read the package, and there are so many resources to do it. Just that in the teaching, I want you to get the basis. Once you know the basis, getting a package to use is just an addition of it, and it's easier if you know the basis than the other way around. But it's good. GG plot, that's where you should be heading towards. Yeah. Okay.
Yes, sir.
Yeah.
Yes, sir.
Okay.
Thank you.
You're welcome. Okay. Any question again? Okay. All right. Then we move on. Okay. So that's the D part. As I said, there will be so many ways you can do it. But we've gone through this to know that you can separate, you can plot, you can superimpose, you can get your legends and what have you. Okay. Even the statistical formulas and so forth, we can use expression to get a statistical formula on our plot and so forth. So there are so many things you can do with this. Okay. So the D part, we are done. I'm moving on to E. Any question before I move on? So E says, what can you say about the relationship between the total length at capture as and the OTLIF age at? I think that's what we've discussed it already. So E, we've already discussed it from the first plot. So we can move on to F. F is that construct a histogram for the total length of OTLIFs and color the bars. Also provide relative frequency. What can you say about the distribution of? Okay, so that's just histogram. I think we all know how to do it, but for the sake of our discussion, let me just do one. So histogram, we use what? Hist. Quite easy. So you come here, you can, of course, use some few observations. What do I call it? Arguments. Okay, so just some few arguments. What is X? We just want the length. So we go here, we select the length, and that's we don't want a title for it, and we need X lab should be what? Length. We can go up there and copy the length. It should be this, length in millimeter. So we paste. Now let's do this and see. So there it is, the frequency. So what can you say about the distribution of the total length of OTLIF? Hey, it said we should color,
to
right?
the right.
It looks what?
Skewed to the right.
Skewed
to the left.
Skewed to the right, skewed to the left. Which one should we take?
Skewed to the left.
Skewed to the left. Why do you say so? Yes. Why do you say it?
Because when the easiest one is to see that the tail of the distribution is pointed towards the left. Okay.
So what these are things that let's say those are the Fisheries Commission will be looking at. So as a statistician, if you plot this and you want to explain to them, you just say it's skewed to the left. What does it mean? Yes.
The median and then the mood are around. We can say they are around. In fact, the median is between 55 and 60, between that bar. But then you can see that the mean the mean is less than those values.
You can see all that in this graph.
No.
There you have eyes, so we need some. Okay. Explain it in a layman's term.
Usually, if a distribution is skewed to the left, you have say most of the observations on the mode and the median and being taking higher values, but then you have a mean smaller values which are
still talking statistical terms. You just have to explain it in a layman's point of view. So you don't use statistical terms again. You said it's skewed to the left, good. But what can you say? If I'm going to cut Otilif, what should I expect?
Doctor, if you're going to...
If I'm going to catch some of them in the river, what is my expectation of the total length? What is likely?
It should. Okay. So it should be between, say, 55 and 60, around that number.
You are close, but not quite. Yes. Yes. Other people. Who was talking?
Benjamin.
Okay. Bismarck. Bismarck, unmute yourself. What can we say about the distribution of the Otilif length to a layman? Bismarck doesn't want to unmute. Okay, Dan.
Good evening.
Yes.
As the total length increases, there's a high frequency that you catch the fish in the way. So as the length increases, the total length increases, then frequency also increases.
What does that mean? Your destiny is perfect. Is the name perfect?
Hello, Doc.
Yes.
Please, the maximum fish. Well, we can say that during 55, the length at 55 and 60, we can catch the maximum fish there. But when we move forward, it starts to decline. So that range will give us the maximum stock that we need.
The maximum what?
The stock, as in the fish. When we are using the fish as an example, maybe the depth of the sea will get the
my friend, we have total length, so stick to that. Don't generalize it.
Okay, sir.
So they caught the fish from two different rivers. Each of them, they measure the length.
Okay.
And we have this distribution. So how are you going to explain this to, let's say, a fisherman? That's all I want. So you got to, let's say, Jamestown, and then the fisherman, you are explaining this to them. So you can just say that most of the fishes that are caught in the two rivers, they have length because those with lower, shorter length are lesser than those with what? Longer length. In other words, you are more likely to catch a fish with longer length in the two rivers. Generally, that's it. But if you want to bring in some numbers, you can also say that there are more fishes with length above 50 than below. That's also accepted. But in some cases, maybe when you talk to the fishery scientists, they may have a postulated average length for those species. So then you can look at it and use it to now guide you as to how to interpret it. So what this tells us is that in as a statistician, you may find yourself in any field at all, right? Once you find yourself there, you have to learn the terms, but the basic understanding of your graphs and so forth, you must carry it with you. But you have to interpret it in relation to the problem at hand and what is required in the field. But this one, what it says is that we have fishes that have longer length are more than those that are with what shorter length. That basically that's it. Fishes, is it okay?
Yes, look.
Okay. Any question on this? Okay, so these are basic things, but they are very important. As I said, those difficult things, you will not see them or you will not encounter them very often. But the basic ones, you need to grasp them quite well so that when you are analyzing a data set, you don't write things and then somebody is there canceling it and so forth. And you should be in a position now to be correcting people, because you now have a better overview of statistics than, let's say, an undergraduate student. Okay. All right. So I think that should be fine. We should move on. Yes.
Can you also say that the fishes that are longer in length are more older than those shorter in length, since it is comparing the age and the total length?
We haven't added the age.
Okay.
This one is only the length. But remember, we did this. If you are linking it to this one.
Yeah.
Are you linking it to this one?
Yeah.
Yeah, but look at it. This if let's say 2.5 will be the middle. If you check, it is debatable, but I think no, those.
Yeah, but 3, 4.
Yeah, 3, 4 will be more than So yes, when you are doing a total, overview of the data, you can link it so that you get a story to tell.
Okay.
Yeah, but the histogram is just about the length.
Okay.
Yeah. Okay.
Okay.
Thanks. Okay. So now we've constructed a histogram. We say relative frequency. That's also important because so the relative frequency, all you need to do is to just copy the same thing, but you need to add, I think, freq is equal to if false, right? Okay, so this will now give us, so the frequencies will now be probabilities. Okay, so that's the only difference. So this is the relative frequency histogram, and the other one is frequency histogram. I said you should superimpose what? Construct to provide really. What can you say about the distribution? We've talked about it. Superimpose a density plot of your histogram in F. A density plot on your histogram. Comment on what happens between the first and the second histogram. Okay, so okay, so okay. Let me see. You see, I can why did I ask this question? Well, you see, later on when we talk about estimation, we may be fitting the distribution to this data. Usually when you fit the distribution, I'll ask you to superimpose the distribution on the histogram so that we know that, okay, the histogram we are, what do we call it? The distribution actually fits, or the data fits this distribution better than the other. Okay. Now, the tendency is that when you are fitting the distribution, you use this. So that's why I brought this exercise. So let's see if I want to. But okay. So there are two things. Let me see. I need to get the length, but I need to you need to find the density, right? So density of this, if I do this, it is just going to list them like this. If you call density, it just uses a bandwidth to just fit a histogram to it, okay? Sorry, to fit a density. So what I can do is that I can use lines, okay? So my x, but we will have some problems, but we'll get through it. So y will be your density. X should be this one, the length. But because it is not okay, let me do it first, and then I need to color it. What color will even be better? Let's say blue. I think we will not have a good lines because of the yeah. Wait. Okay. We should be able to plot this. Okay, so I should be able to lines that over this. Okay, yeah, so this is what, just the lines of the density like this. Okay, so this is the density one, but let me go here. What do you think will happen if I superimpose the density here? Let me color it. What do you think will happen? Look at what we've done over here. We want to now superimpose the same density here. What do you think will happen? I mentioned this. Okay, but let's see. Why do you think it's like this? You see where the blue line is? So this is the same thing you will encounter if you want to superimpose density on a frequency, because this should be a probability, and this one is frequency. So the thing is between 0 and 1, and you have 15 over here. So what do you expect? It will be on the almost the 0 line. Okay, so you have to be alert on this if we want you to superimpose a distribution on a histogram. It can only be the relative density or the relative frequency. Other than that, your density plot will be on the x-axis, and you may think it doesn't fit the distribution well at all. Okay, please, is everybody okay? Please, are you there?
Yes, sir.
Okay, so please note this.
We are here.
We will come back to it, and in exams, most people will do this, and then it means you don't really understand what you are doing. Okay, so please take note of this. When we say superimposition of a density, you cannot superimpose a density plot on a frequency histogram. You will get what? So that's the essence of the exercise that I talked about. And then as a comment on what happens between the first and second histogram. So the first one, because it's frequency, you see all your density on the x-axis. It's like it's 0. But when you superimpose this on this, you actually see the actual distribution on it. And this one is a kernel, so it's not like it's just a non-parametric way of fitting the distribution, a kernel density that it uses. And we can change the bandwidth so that it follows the data, or it's smoothing it well, and so forth. So that's it. So that's it with the first question. Any question on this?
Yeah. Hello, Doc.
Yes.
Yeah. My name is Rich Monado.
Okay.
I just arrived home, and I want to ask for a clarification on the superimposing the line or a density function on the histogram.
Yes.
Please, are you saying that we can superimpose on a relative frequency distribution?
Yes.
And not on the normal frequency distribution.
Yes. You
okay.
Yeah, because there, this is not a probability. It's just frequency. Right. So if we divide it by the total, then we are in a position now to superimpose a density plot on it.
All right. Yeah. Thank you.
All right. Okay. Thanks. Any question again? Okay. So let's try and add some more. Let's say G will be that we want to find out. Remember, there were. Oh no, I think let me see. There were 3 questions, right? 2. Let me see. Okay, 2 uses another data, but maybe let me add. Oh, it was FG. So what we did was G rather. But what can you say about the distribution? Okay, it's fine. G is what we did with the lines. So this is not F. I think we did not do one of them, and we did it, but I did not add it. So H rather. Remember the fishes were taken from 2 rivers, right? We've done it here. It was what were the rivers? I think Trent. No. Yes, Salmon and Trent. Okay, so let's look at the characteristics of the length of the fishes in the 2 rivers. Do we have one of the rivers with maybe longer octave or are they the same? So let's look at it that way. So we want to compare the distribution of octave length in the two rivers. Now, what do you think we can do to check this? We've seen the entire distribution, but we want to find out what is the distribution of the length from the two rivers. What do you think we should do? Yes. Let's speak up so that we can do more. We have two rivers. We've taken fishes from the two. We've checked their length. We know the distribution of the entire fishes from the two rivers. Now we want to be able to compare their length from the different distribution. What do you think we should do? Robert. Robert or Obed, can you try? What can we do? No one. Okay, I see Robert is typing. Sarah. Sarah, what do you think we should do to be able to compare the length of fishes from the two rivers? Hey. You can't unmute yourself. Oh.
Hello, Doc.
Yes.
Hello, Doc.
Yes.
Please,
the one shouting in the background should come and answer the question for us. Okay, please go on.
Please, can we plot it on maybe a compound bar graph?
Why should we do that on a compound bar graph?
That one may give the component of both rivers, the fishes from both rivers, then we can compare them there.
So the question is, why are you choosing a bar graph? You have to ask yourself, basic one, when do you use a bar chart? What data type? Do you need, do we use bar chart on? Is it quantitative or qualitative? Yes. We should find mean of both rivers. Yes, we can do so, as Robert was saying. But what about the bar graph? Oh, please let's discuss, okay? If I'm just answering all the questions, then but this one will stimulate. If you are wrong, it's okay. It will just help us to correct you so that you don't.
But I think the bar graph is used for categorical data. So maybe you can use the box plot to plot the box plot as a function of the type of river.
The type of river, good. So that's a good one. Okay. What else can we use? We can use a histogram and so forth, but a box plot will be the best thing. Because that one we can just compare it straight after with each other. Then when we finish, we can also do some descriptive statistics on it. Okay. So let's go back. Please, is everybody okay with this? Okay, so we want to do a box plot to help us compare them. So we do a question mark for box plot. We need to use this one. So I copy. I need the data. So what is the data? This one. What is the formula? So in order not to make a mistake, I go back to the help files, I go to the data. We are plotting what? TL as a function of what? The river. And it's like this. If we want to color it, we can color. Maybe red and yellow. Okay. So what can we say about the distribution of the length, right? And well, we haven't, we can do the Y lab. It's, we go here and copy total length in what? Then. So now how can we, what will be our comment on the distribution of length of fish or leaf from the two rivers?
Have a longer length than those in the Salmon River.
Okay. Okay, that's one observation. Yes. Who else? Okay. So that's it. But what you said, this is descriptive statistics. So in order for us to be able to make conclusive statement about this, what should we do? Yeah. So for us to be able to decide on this, whether salmon and Trent, the length from there are different, we can conduct a t-test. So we go and check the health files for t, and we can use this one. So t-test, the formula will be the same. Data is the same as this. So I just copy this and paste. There we go. Please, are you following? So, yes, whenever you have to answer questions, nobody will be telling you that test a hypothesis when you are in your workplace or you've gotten some consultancy or whatever. They want to solve a problem that whether the length within the otolith cut from the two rivers are different. So you do this. So well, two sample t-test. Okay. So what does it say? The data is what? TL by the river. Okay. T is equal to this. Degrees of freedom is that. P-value is that. Remember that in doing this, I'll actually check whether the variances are the same or not. Remember this t-test, it has var.equal. So for us to be able to do that, we should have checked. But when we use the formula type, it just takes, it does it automatically. Okay, but we can check ourselves. So let's conclude. When we finish, I'll come back to the test of variances, because that will be important when we are doing an over test as well. Okay, so if you have watched the video on the two sample test, this is what we mean. Okay, so there it is. Our T is this. Degrees of freedom is like that. P-value is this. Remember I said that in the video, there are three ways we can use to make a decision on a hypothesis test. One is the p-value. So the p-value, what is our criteria? So making a decision in hypothesis test. So A, so the p-value, we are going to say if p-value is less than alpha, what do we do? Reject H naught. So in this test, we assume that the usual one is 95%, which means alpha is 0.05. So what is our p-value compared to alpha? So we will say that since this p-value is less than alpha, which is what? 0.05. What is our decision? What will be our decision? Yes.
We reject
the null hypothesis. What will be the conclusion? What will be the conclusion?
That their lengths, there's a significant difference between the lengths.
Yeah, so there are significant differences between the length of fishes. So you interpret it in relation to the data. There are significant differences. Yes, differences between the length of fishes. Oh, not fishes, it's otolith, right? Otoliths caught from the two rivers. So that's basically what we'll do. So that's one way. B, we can also use the confidence interval. So if we are using the confidence interval, what will be the criteria? If the interval encloses our null hypothesis, we fail to reject. If not, we reject it. So look at this one. The alternative is that the true difference in means between Simon and Trent is not equal to 0. So we check the 95% confidence interval. Does it include 0?
Yes, it does.
Are you sure?
Oh.
No,
It does not.
It does not. So what do we do?
We reject the null hypothesis.
We reject the null.
null.
Yeah. So since we can write that since, then we put this one into brackets, since, like this. Since the 95% confidence interval CI this does not include or does not enclose 0, we reject H naught. Okay, the rest is just like the one we did previously. Is everybody okay with this? So the conclusion, we've already done it up there. Any question on this? And then lastly, using the test statistic. So if we are using the test statistics, then we know our test statistic from our sample, from the sample, T is equal to this. So we have to read the critical value, right? So the critical value, and then in this case it's two-sided, so we'll reject for very small, very large values. Okay, so how do we do that? We have to read K of T. So you need the quantiles. So there was a video I said you should watch. It's just a 17 or 15 minutes about probability distributions in R. All these are explained in it. It's not anything. So we copy this K of T, the T distribution. We can take this one off. I'll explain the lower tail, so I'll leave it. Non-central value, we can take it off. So the degrees of freedom is already here, 39. And then P. Because it's the lower tail, I'll choose 0.95 so that it will go to the upper tail. Right. Or I can use 0.05 because this is negative. I'll use it because the 0.95 will give me positive, 0.05 will give me negative. Why is this so? Because when you draw your curve, the T curve, on the left hand side is what? Negative, because 0 is over there. So that's it. So here, what is our criteria using the test statistics? The criteria is this, that reject H naught if, right, because it's two-sided, T is less than negative, or just T, in this case 0.05. Oh, sorry, it should be 0.95 rather, because 0.975 or 0.025. So it's not this, but it should be 0.025 like this. So it should be negative 2.0, not 1.65. Okay. So 0.025, right? the degrees of freedom. In this case, there are 2, but this one we have to use the formula to calculate the degrees of freedom, right? It is not, the other one would have just been n1 plus n2 minus 2. Okay, that's what we use. But in this case, we have to use the formula to find that one. So let me just say df, right? Or if t is greater than t, this would have been 0.975 of df. So that's it. This is what in the basic statistics you use as your p-values. Test statistics to be able to. So these ones, once we've seen our critical value, is this. So that t that we read from tables, that t, let me go back. This t, right? This one, in this case, is what, 39 point something. 39.884 is equal to negative 2.02, right? So now you check negative 2.02 and this one, which one is smaller? In other words, is this t on the right hand side of this or left hand side? Yes. Left hand side. So what do we do?
You reject the null hypothesis.
You reject the null hypothesis. Yeah. So that's it. So the same this one, you have to give him the certificate when you finish. or next 2 weeks when you are coming to class, bring him. He must come and do statistical computing. Okay. So in the same way, like since t, okay, this t is less than this, right? That's this. What do? We reject. We reject H naught. Okay, like that. And of course, the conclusion will follow like above. So any of this we can use to what? To make a decision on a hypothesis test in this. Okay. So that's it. So now we can conclude that differences that we saw here, okay, is actually significant. Okay. Is everybody okay? Yes, please ask. But we are losing you. I can't really hear what you are saying.
Please, is it okay now?
Yes, it's okay now. Oh, we are losing you again.
You run your t-test.
Yes.
And then you look at your degrees of freedom and then it is a decimal.
Yes.
Is it in...
Yes. And that's the next thing I want us to do, to check. So this will be what? I think L or something. The variances of the length of the octaves.
Sir.
Yes.
Please, I also have a question.
Yes. Please, you can go on.
My question is on the graph, the
box plot.
Yeah, the box plot.
Yes.
You see that someone is bigger than trend.
No.
I don't know.
No.
I think the width, the height is.
The height.
Yes.
No, you see, this box is above that one, even though they overlap.
Yes.
Yes. So if you look at the median over here is around 50, maybe 7. Over here is around 52. So the median in this place, so if you check even the first quarter for the trend is even higher than, or the length is longer than the median of the salmon.
Okay.
So that difference we are seeing, the test is confirming that it is what? It is actually significant. And if you look at this box, okay, none of them actually deviate from normality so much. We don't have any outliers, even though they are not really normally distributed. If you look at trend, you see the whisker is longer. All of them, the whiskers are not even. So there's some sort of skewness in it, but I'm not sure it will be too strong enough to reject normality.
Yes, sir.
Yeah.
Thank you.
All right. Okay. So now let's see if we were. I made a comment that we should have actually tested whether the variances are the same. So even though we've seen it in there, let's test it. So to test that, we use var.test. So you can check the help files for var.test. So it's an F-test to compare variances of 2. Later on, when we get more than two groups, we cannot use the variances. We cannot use var.test. So we'll use Bartlett test. There are other tests that we can use to check when we are doing ANOVA, to check whether the assumptions are satisfied. If it is not satisfied, what do? We use the non-parametric version. Okay, so let's see. So here I can just go and copy. You need X and Y, so I just come here and copy where X is. We've done this. Oh, okay. So, yeah, I should just use a formula like that. That also works here. Like that. Good. Okay. So here, this is a test of variances. So it is just S1 squared divided by S2 squared. The variance, when we divide them, if they are the same, we should get 1. Right? So in this hypothesis, you are saying that the ratio is equal to 1. That's against the ratio not equal to 1. So we will reject for large and very small f values. So let's see. In other words, we can also check whether the confidence interval encloses 1. If it encloses 1, what do we say? Yes, they are not significantly different. If you look at this one, you should see that it's not quite different from 1. And look at the p-value. The p-value is so large. Okay, so that's it. So the variances are the same. So I could have done this, okay, by the t-test. Okay, I can go back and do this t-test. Oh, why is it that when I roll it, I'm not getting this one? Okay, so I could have just done this t-test by stating that var.equal. Okay, so when you use the formula, it doesn't really, let me see, I think it won't. Yeah, it did. Okay, so Yeah, so we could have done it like this. And it actually uses the two sample t-test. Okay, so you see now the variances has changed. Sorry, the test is different. So when the variances are not significantly different, we now use the n1 plus n2 divided minus 2. Okay, but when we use the formula, it just takes the Welch one. It assumes that the variances are not the same. That's why we were getting the degrees of freedom as 39 point something. So in R is not like SPSS, where when you are doing this test, it will provide you with all the alternative like variance equal, variance not equal. So here you need to be checking. Okay, before you do your t-test, you check whether the variance, that's checking the assumptions. And at the MPhil level, you should know that when you are doing tests like that, you need to check the assumptions. So for example, you need to check whether there is normality within the data. Okay, we haven't done all that, but now you can do so with the Shapiro test. Okay, so you test the Shapiro-Wilk normality test. You can test to see whether your data follows normal distribution. If it doesn't, then you use a non-parametric version, right? And so forth. So you have to always check some of this before you look at you do this. Okay, so your normality test is also the results is like this, and then you interpret it. So please, at this level, as I'm saying, tests are important, but before you do a test, you start from the descriptives. You check descriptives so that you can describe the data to the reader or whoever you are doing the test for before you come to the test itself. The test will have assumptions. You check the assumptions to make sure that they are satisfied before you move on to do your test. Okay, now if the assumption is not satisfied, what do? You can use a non-parametric version. So for example, here, if we think the results is not satisfied, we can use a Wilcox test. That's a non-parametric version of the t-test, whether one sample or two sample. So Wilcox, it performs a 1 and 2 sample Wilcoxon test on a vector of data. So we can use that one to do it. And so forth. So that's it with that part. And I think this actually, with this discussion, it actually captures what we would have done in 2. So you can take the 2 as an exercise and do it. Then 3. 3 is what? The BGHR fish is a data frame on so and so big field in a reservoir. Use appropriate graphical approach to study the relationship between weight of fish and length. It's just like what we did. You plot your... Let me now move from R so that we can discuss the questions. I think we've done enough. And it's getting late. It's 8:30 in Ghana now. So, I have shared the same thing. And it's almost 11 here. So I must... let's see. Good. Okay. So, yeah. So, use an appropriate... We've done one of them. It's just a scatter plot, right? Okay. So the first one is just scatter plot that you need to do. The next one, test whether there is a significant correlation between this. Okay, so this I have to do it. Did we do a test on correlation? Have we done some?
No.
Not yet.
No, we didn't.
Okay. So
Yes.
I think that's why I brought this. So let me quickly. It's not that difficult. Remember that the correlation coefficient, you can use a t-test to do it, right? Any standard test in statistics, you will find this in there. Okay. So let me quickly go here. Then we try and do 3. We should be fast, and then so question 3. Okay, so first the data is BGHR fish. Okay, so this is it. Data on so and so. We can look at it if we want to see the way it's quite. This is longer than the other one, right? Okay, you see that there are some NAs in there. So when you are doing anything, you have to be careful what you to expect. Okay, so we want to plot x. What was the question? We have to test whether there is this first of all, weight and length of fish. So we call this x is I think the length. So length. And then y will be the same thing, weight. So we do weight. Okay. Of course, we can get S lab, which is length. And when you come here, you will see length in millimeter. Total length in millimeter. So please, let's cultivate that habit of, labeling such that as I said, I don't want to see any dollar sign in any of your work. Okay, it's not a good thing because not everybody you are dealing with to know what R is, to know that dollar sign is for selection. Okay, so this is it. So, of course, what can you say about the relationship between the length and weight? Quickly, what can you say about the length, the relationship between length and weight?
So we can see that.
We can see what?
The relationship of the relationship between the length and the weight is positive. That means a fish with higher length has more weight and vice versa.
Okay, so there is some positive correlation between them. As one increases, the other increases. So in the other, if you catch a fish with a longer length, you expect it to have more weight than a fish that is shorter than it. Okay. Now to test the correlation, we use core.test. So let's look at it. So core.test is like this. Okay. So it also uses formula. So we can take the formula and the data and use it. Okay. So what is the data? We know the data. Oh no, this is not for 2. So yeah, I should just use X and Y. There's no need. I'm not going to use the formula. X and Y already done. Then I don't need the data. Okay, so like that. Okay, we've done hypothesis, so now we should be able to interpret this quite easily. So here we are only checking whether there is a relationship between. So if there is no relationship, rho will be what? 0. So this is it, and we are using the Pearson. Of course, there can be the Kendall or Spearman if you want to, and alternative is two-sided. So that's it. Okay. So this is T. We can use T. We can read the quantile values and check it with this. But there's the p-value. Look at the p-value. So what will be your conclusion if you are using a p-value?
P-value is significant, so we reject H0.
We reject H0, yes. And the H0 is that there is no correlation. So what can we say in conclusion?
There is a strong relationship between the length and weight.
Yes, there is a significant relationship between what? The length and weight of the big whatever the fish. Okay, if we are using a confidence interval, this is it. So if you look at it, the 95% confidence interval is from what? 0.84 to 0.91. Now, if you are using a confidence interval, what will be the criteria?
You check if it contains 0 or not.
Good, yeah. Does this contain 0?
No.
No, yeah. So we reject the null hypothesis and conclude the same. So that's how you do correlation test in this. So that's it. Let's see. That's the C part. Then in order to estimate the weight of fish, fit a linear regression. Okay, so these are all simple stuff. We can also do a regression and check whether the regression is significant or not. So once you do correlation, you move on to regression. So in R, we use LM for linear models. Okay, so fitting linear models, you use LM. Okay, so basically a formula, the data. So we know how to use the formula and data. So basically that's it. So I copy here. I come and then paste it here. Okay, and I'll delete this and so forth. But here we need to, let's say, fit a big. It was big something. So let's just leave it that big like that. So what is the data? I need to go here and the big whatever fish. Then the formula. What do I want to do? What I need is weight as a function of what? Length. So I copy that one. You see, I'm copying. So in that case, you won't make mistakes. Then you run this. Okay. If you want to see the output, you use summary. Summary of the name you gave to your, and then we get the results like this. So what we have done is to fit a linear model or a simple linear regression. If we have more data, we can add it here. We add it plus, and then it becomes multiple regression. So you can go on and on and on. Okay, but this is simple linear regression. So when you look at the regression output, you are going to get what? The residuals. Remember, residuals in regression is good. That's what you use to test whether your assumptions are satisfied and so forth. Okay, but what do we want? We want to know the estimated line. So the beta naught is negative estimate of the intercept. Intercept is beta naught. Then the slope is what? 3.2, or the beta one is 3.2 something, 3.28. The standard error is this. Okay, for each of them. When we want t value, if we want to check whether the, okay, so I may have to go through this maybe on when we meet the Tuesday. Yeah, but basically this is the output. Here we can, I'll explain again. If you want to, we can check whether H naught beta naught is equal to 0 as against beta naught not equal to 0. In other words, should we include an intercept in the model? And this test, the p-value is very small, so you reject H naught, which means the inclusion of the intercept should be done. Then here we can also check whether the slope, in other words, is weight of fish related to the length, right? Okay, we can do so by stating that beta 1 is equal to 0 as against beta 1 not equal to 0. And this 3 is significant because the p-value is very small. So we must maintain this equation. Okay. And then here, it gives you the significant levels where, so even at 0, 0, 0, 0, almost 0, you are still rejecting. Then these are the residual error, the degrees of freedom, okay. And it says 91 observations deleted due to what? Missingness. Remember there were NAs in the data, so it takes it out. Then here, you have R squared. What is R squared? It's a percentage of variation in the dependent variable. In this case, the percentage variation in what? The weight of the fishes. Okay, that is explained by the 8th regression on what? The length is what? It's 78%. Okay, and the adjusted one, we won't see much difference here, but when we get to the multiple one, you see much difference. So the adjusted R squared always adjusts for what? The correlation between what? The variable you are bringing in and the dependent variable. Okay, and we can use this F2 as the overall F test. So remember, linear regression, you can get an F table or an analysis of variance table where you divide the sum of square errors into a sum of square regression and sum of square residuals. Then from there you are able to get your mean square regression, mean square error. You divide the mean square regression by the mean square error, you get your F, okay, and that p-value. So under the simple linear regression, the F test is the same as the lack of a test, and is the same as checking whether this beta naught is 0. Okay, so whatever conclusion we get from here will be the same as what we get. But when we get to multiple regression, it will be different. Okay, because you have to hold one of them constant and then you use the other one and so forth. So basically, that's how we do regression in R, and this is simple linear regression. As I said, if you want multiple linear regression, you just add on to it. So for this data, if we still want to check explain the weight, maybe if, let's say, count of fish is also related, or let's say the specimen, they are all categorical data, but we can have, what do we call it, multiple regression with what? Categorical data as well. Or let's say count. If I want to add count, all I'll do is to do plus count, and then I rerun this regression. Once I do so, you will see that now I have two variables. So this is a multiple regression, and it doesn't even come at all because we have NAs in there. But let's see, count of fishes in that weight. I should have used this one, but that's categorical. So you're going to get different, what do we call it? Let's say graphs for each of these one. Yeah, so specimen code, this is it. It's also significant and so forth, but its interpretation should be different because you have to move within these values, and it's just numeric code, but I'm sure it is not it is code, but it has not been factored. If we factor it, we are not going to get the same thing as I have done over here. But this is just to illustrate to you that we can also do multiple regression and be able to interpret them and so forth. And if you look at the R squared, remember we had 78. So once I added the spec code, you see it has now jumped to what? 0.9085 and so forth. So when you add more variables, you tend to explain more of the variation in your dependent variable and so forth. But we will get back to this in our next meeting. Okay. Any question on this before we call it a night? Okay, so please, you can continue. The next one is predict. So you just use the function predict, but the small letters, and you can actually predict with new data. So you put in the data. Then we talk about so it's for specific lengths, and I asked you which of these predictions are reliable. The key thing you need to look out for when you're answering that question is to check whether your S values actually contains the value you are actually predicting. So if you look over here, 700 is not within this range. So if you predict, its value is not reliable. Okay? Because look at what is happening. It is possible that if we have 700 to go up like this, but the line may increase, or maybe biologically, if you get beyond 300, maybe your weight start coming down. But because we don't have data there, you can't tell. Similarly, there's no yes. Please, are you asking a question?
Yes, sir.
Yes, please, you can go on.
I wanted to know, with a software like SPSS,
yes,
the output will be displayed in a tabular form.
Yes.
So with R, are you going to do your own tables or what?
Okay, so R will come like this. So if you want, you can do a table, but in your work, if you have stated that you are using R, then you can get this in a box and tell the reader that this is the results, and then you go on and interpret. That's how it is. So
okay,
yeah, you just like the way we were doing, you just put it in a box and you say this is the R output, and then you explain. That's it. Yeah. But this is also key, as I was saying. So the 80, there's no 80. So it is possible that this curve, when it gets here, may go up, but you won't know. Okay, so you only believe a regression output if its independent variable has been, it's within the range of the values you are dealing with. So that's it with my comment on that, and you can do so as well. And then compare the weight of fishes for the various species. I think the E is ANOVA, and maybe in our next tutorial I'll take that and multiple regression, and then that should be it. I'll spend just some small time on that, and then we can move on to estimation. Okay. Any question? So I'll end it here, and I'll get a video sent